welcome to lecture 1.6, Robot, Artificiality, and Artificial Life. We have claimed a necessary quality of a robot is that it is artificial, i.e. designed by humans. We include here robots designed by robots, designed by robots, designed by robots, designed by humans, okay? So as long as the original robot that begot further generations was designed by humans, these offspring are also considered artificial and therefore robots, if they also meet our other criteria for a robot, such as intelligence. Robots designing robots. What does this mean? A field of interest to many roboticists is that of artificial life, which is the interdisciplinary study, including biology, chemistry, computer science, robotics, etc., of life itself and its artificial creation. The term life has no universally agreed upon definition, but certain features have been suggested as necessary, such as the following. The first is appearing lifelike. So this is a tacit requirement for many people. Despite its apparent banality, this is perhaps not to be overlooked, for it is plausible that the meaning of a word is its use in the language. This has been taken to heart by artists such as Theo Jansen, who has created Strandbeests, wind-powered kinetic sculptures that walk on the beach and appear lifelike. And I recommend that you check out those Strandbeests on the internet. There are some really beautiful videos. This perspective is limited, however, since it doesn't elucidate the meaning of life to say that it is what appears to be life. Another common requirement or necessary condition for life in a lot of people's view is self-organization, which is the process of local interactions of a disordered system yielding global order. Emergence in robotics is a form of self-organization. We've previously talked a little bit about emergence. Examples of self-organization include ant colonies, crystal growth, and lasers. So not everything that is self-organizing is considered to be life. For instance, crystals aren't usually considered to be life. But this is often seen as a necessary condition for life. Self-replication is another. It's the process of an entity creating a copy of itself, perfect or not. Of course, these copies would usually also be capable of reproducing. Natural selection is another. It's the evolutionary process that requires both variation in self-replication and the natural survival and reproduction of those offspring that are better adapted to the environment. And finally, autopoiesis, which is the fundamentally cellular logical loop that posits its own constitutive self-environment boundary as being caused by itself. Or, as Zizek has it, life emerges when the external limit of an entity by its environs turns into self-limitation. The picture that goes along with this is one of the little constituents of a cell. So we've got things that look like that inside the cell, building its own cell wall, okay? So autopoiesis is this process of building its own boundary, an entity building its own boundary, which of course there's a little bit of a loop there, something that builds its own separation from its environment. So it is, however, understood to be one of the ways that life can be fundamentally described. Others suggest no such general qualities of life can be established. Wolfram is an example, Stephen Wolfram. Because our definitions are always relative to our own human perspective. One wonders, however, what more one could hope for from any definition. Cellular automata. Early researchers into artificial life constructed abstract models of life from small sets of basic rules. One such model is the cellular automaton, which is a set of abstract cells in a grid of any finite dimension, such that each cell has neighbors, which is to say, is adjacent to others. We can think of this in 2 dimensions as being a simple 2D grid. Where each of these boxes would represent a cell, okay? So this cell would have neighbors here, 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 and here. Depending on your definition of neighbor, it could also include these. So these are cellular automaton, acellular automaton. Each cell can be in one of a finite number of states. A set of rules determine the new state of each cell at each discrete time step from its previous state and the previous state of its neighbors. So this cell, we would find out from the rules what its new state's going to be from its current state and the current state of these neighbors. Okay, so depending on the definition of neighbor and depending on the rules for this cellular automaton. Therefore, in non-stochastic models, so in stochastic models, there can be randomness in that generation of the new state. But in non-stochastic models, a given initial state or initial condition, together with a set of rules, results in a deterministic process. So set the initial conditions, it will evolve from there, it will proceed from there in time, and the rules will just will always work out the same way. So if you went back and started with the same initial conditions, you would have the same identical steps every time. In Conway's Game of Life, a 2-dimensional cellular automaton, the 2 states are taken to be simply populated or empty. So in this one, we have a 2D grid again, so it looks sort of like this. But each cell can have only one of 2 states, and those are taken to mean that a cell is populated, that's one of the states, or a cell is empty. The game has the following simple rules. For a space that is populated, each cell with one or no neighbors dies, as if by solitude. Each cell with 4 or more neighbors dies, as if by overpopulation. Each cell with 2 or 3 neighbors survives. For a space that is empty or unpopulated, each cell with 3 neighbors becomes populated. So it's almost as if the its neighbors generate more of themselves in the empty cell. Somewhat surprisingly, very complex patterns emerge in this simple game. An example of what a game can look like is shown in figure 110. So here we have red cells, which are populated cells, and gray cells are not populated. And this is just a snapshot in time. This is a game that I played, and I encourage you to play your own games as well. So here's a website that allows you to play it online. And then there's another website for an app that's created, a free app that you can download and play locally. So I actually have downloaded it, and it is here. So this is a starting initial condition that comes along with the Golly app called Glider Stream Crystal. And if we just run this, we will see this evolution of the game, okay? If we stop and reset it, it's the same initial condition, and run it, the same things will occur. There are really interesting things going on here. There are stationary points where there appear to be these sorts of spaceship or shapes that leave from them, and they seem to collide with each other, these different moving shapes, and they sort of create and destroy themselves. They send off these little flame things that sometimes will meet and move together. All kinds of cool things are going on there. There are some that are just stationary colonies that just become stable, right? You see also these oscillations are stable. There's nothing that is going to ever change about this pattern where they just repeat over and over again. That's one of the interesting things that emerges here, is that you'll see stationary little colonies emerge. You'll see motion of colonies that'll move around together when they hit each other. Sometimes they merge, sometimes they destroy each other. All kinds of interesting stuff happens. This app actually allows us to draw in our own. So we can draw in, and it pauses, lets us sort of draw in our own and lets it emerge from there. So we see that we created some stationary colonies, and also we introduced this element that's going to really disrupt the pattern that's gone on around it. So as you can see, it's no longer symmetrical. We are creating things that were not happening before. And interesting things happen. If you do just a little blob, depending on the shape of the blob, you can have the blob turn into something that's stable. You can have the blob also sometimes will just destroy itself. Depending, oh, there was one I created that destroyed itself. A long line will create interesting things as well. So that was a long line, and there's all kinds of really cool stuff. So it's one of these games where you can sort of play with it for a long time, see if you can gain any insight into how this system works based on the very simple rules. Notice that this entire region that we had earlier, replicating this pattern of sort of spaceship looking things going back and forth, like we still see at the bottom right, those are essentially all stopped now. Oh, the by hand sort of drawings that we did, where we created some new initial conditions, have disrupted this entire process. So we still see some interesting activity going on here. And by just these simple rules and different initial conditions, we can create entirely new and interesting cellular automata, and it's very beautiful and very fascinating. I encourage you to each try this out and play with it. It's something you can do for hours in my experience. So one such cellular automaton is called John von Neumann's universal constructor self-replicating machine, which works as follows. Consider an automaton system containing the following elements. A description, let's call it phi1, of this system, sans or without the description itself, okay? For it cannot contain both itself and other automatons. So we want to have a description that describes this machine, but we can't have a description that describes the machine and itself, because then it would always need more space and it would have an infinite regress. So we can't have that. So we have a description of a machine without the description itself in the machine. All right. Another element here, a universal constructor that can read a description of an automaton and construct it. Okay, so if it reads a description could be encoded in different ways. So if you have a simple two-state cellular automaton, you could have a row in which you have a state 1, 0, 1, 1, 0, for instance. And that would encode potentially a description of an automaton. This first description, it might be one such description. A universal constructor could take any such description and it can create in the cellular automaton some other place in the grid a construction of what the instructions give. The third element that is required is a universal copier that can copy any description of an automaton. So it doesn't read the contents of the description. It simply copies the description itself. Okay? Finally, a controller that applies the constructor and copier. Okay? And it does so in the following way. So let the collection of the constructor, copier, and controller be called X1. So it's the machine sans or without the description included. Okay, we'll call that X1. The original one we'll call X1. So the original machine is X1 along with the description of itself. Okay. The controller commands as follows. 1. It commands the copier to make 2 copies, phi2 and phi3, of the instructions phi1. Step 2. It commands the constructor to read phi3, which actually when you read an instruction but with the constructor, you destroy it. So it destroys phi3 as it reads it and constructs a new machine, sans instructions, and we'll call it X2. So remember, the instructions only include the instructions for the machine without the instructions. So it copies that part of the machine that doesn't have instructions in it. And we'll call that new machine without instructions, X2. And in step 3, the controller ties together X2, our new partial machine, with the undestroyed copy of the instructions phi2. That's why we made 2 copies. We wanted to have a phi2 left over after phi3 got destroyed. So that's what we have. Now there are 2 machines. The original machine, which is the machine that doesn't have the instructions, glued together with its instructions, and its descendant, which we just created, which is X2, which is the new machine without instructions, glued together with its instructions, which are the same. These 2 together are an identical copy, just in 2 different places in the cellular automaton. Okay, now, very cool stuff. A lot of these ideas actually were originally around even pre-computer. John von Neumann was originally working on these without a computer. a lot has happened, but these fundamental ideas of how to have a machine replicate itself are really based on these original works. So, living robots? Lest we seem to be too far afield from robotics, let's return to robots proper, with their mechanical presences. We've examined how a robot might be considered intelligent, but alive? Some researchers not only think it is possible, they plan to make them. For instance, the Autonomous Robot Evolution, or ARE project, is designing an ecosystem for robot evolution. One of the key aspects of natural selection is competitive survival, which requires an arena. This project includes the creation of such a subsystem, along with several others, such as an ecosystem manager, that's actually a robot arm, a virtual environment, and a training environment. This is one among several projects with artificial life as a goal. At this point, few have short-term ambitions to become mechanical, this being one of the exceptions. But the foundations are being laid, especially in simulation. There have been lots and lots of groups working on simulating robots that evolve, that have performance metrics, that then have different simulated environments where they perform better or worse, and then their properties are evolved, are iterated upon. And the term here that you'll see a lot is genetic algorithm. It's another fascinating topic. It can sometimes be seen as being an artificial intelligence topic, but it actually is something that came out of artificial life as a research project. So this is an example of artificial life and robotics and artificial intelligence all being distinct fields, but also very, very intermixed, and there's a lot to learn for each of these fields from each other. So yeah, so that's all I have for you on the fascinating topic of robot artificiality and artificial life.